Good morning, everyone. My name is Tanish Raghuvanshi, roll number 98, third year chemical engineering, and this is my presentation on the topic heat conduction through chemical heat sources in transport phenomena. So we'll start off with our first derivation. So we define the tubular reactor first. Uh, the first zone, which is when Z is less than 0, it's packed with inert spheres. The same goes with the third zone, which is when Z is greater than L. That means the exit zone is packed with inert spheres. And from 0 to L, the reaction zone, which is what it's called, is packed with catalyst spheres. To start off these assumptions that we made to derive this problem is we start off with the ideal plug flow assumption, which is that velocity is constant and uniform and there are no radial gradients. So it only changes in the z direction. Constant properties as well, density and mass flow rate do not change with position as well as time. And adiabatic wall, which means that the reactor is perfectly insulated, and the effective conductivity as well, which means that we use K effective to represent the combined conductivity of the fluid. So we start off with a differential disk of radius r and thickness del z as a control volume. The energy balance, of course, the rate of energy in minus rate of energy out plus the rate of generation is equal to 0. Now we can consider a lot of different types of energies in this. This is a very generalized energy balance. So we start off with the mathematical formulation, which is that the pi r square, which is the surface area, multiplied by the combined energy flux at z and subtracted by at z plus del z, which is the differential disk, and then the volume into the SC, which is the active zone of the catalyst region, which is equal to 0 as stated earlier. Now we can divide this by pi r square del z, and when del z tends to 0, we can take that as a differential derivative, which comes out to be, as mentioned, differential of combined energy flux with respect to Z is equal to SC. Now the combined energy flux can be broken down into two parts: convection as well as conduction. Convection, as mentioned, is rho Cp Vz into del T, and conduction is K effective into del T by del Z. This can be substituted into the equation, and we can differentiate these accordingly, and we get a second order differential equation. For zone 1 and 3, since there are no catalysts, so there is no active zones, so the SC will be 0, and for zone 2, SC will not be equal to 0, and usually it is a function of temperature, but for the basic model we treat it as a source term to be integrated as well. So now we apply these boundary conditions. Now, since this is a second order differential, we can consider the convective term here to be much greater than the conductive term. So that can be eliminated, which makes it easier for us to solve using these boundary conditions only. So this is important as well, because when convection and conduction are both present, convection almost always dominates. So this is what we do, and then we can integrate this single order differential equation and get the constant and get the equation from there. So the second question is that heat is produced at a uniform rate in a catalyst bed between coaxial cylinders. We have to derive the temperature profile for this, and there are values for us to solve for as well. So again, we start off with the energy balance, 2 pi RL. Since this is a cylindrical shell of radius r, thickness del r, and length L, so we start off with the balance at r and then at r plus delta r, and then SC again. This is similar to the earlier question. Now we divide this by 2 pi L del r and take del r tends to 0. So we get this. Again, this is almost exactly what we've done in the earlier question as well, except for the fact that this is a cylindrical shell of thickness del r, and that was a disk. Uh, Apart from that, everything is almost exactly the same. So again, like I mentioned earlier, we integrate this with respect to R, and then we get a term for QR. So now we apply the boundary condition, which is that at inner wall at R is equal to R naught, no heat flows into the core, which is QR is equal to 0. So that means that we get a value for C1. Now we can substitute that C1 back into the flux equation, and we can factor out the common terms to get this expression for QR. So this equation describes how the heat flux increases as we move from the insulated inner core toward the outer wall. Now we can substitute this for in relation to the Fourier law, which is that QR is equal to minus K del T by del R. Again, we can integrate this and find out a temperature distribution, which was what was originally asked in the question, and find the standard form, which is this. Now, by inspection, since the location of Tmax is asked as well, by inspection T is highest at R is equal to R naught, where the log term is 0 and the bracketed term is maximum. Thus, Tmax is equal to T naught. Now, we can substitute the given data as well. We can, in this question, we can take dimensionless quantities as well to make this an easier question for us to solve. So, for example, R by R naught can be taken as a separate dimensionless quantity. So that is something that could be done so to avoid the tedium that is involved in writing the entire expression. Now the numerical problem, the units are all different, so we have to convert that into the traditional units, and then we can use the formula which is mentioned here to find out T1, which is 874. Due to the difference in conversion, it is slightly different. Now, what if radius was doubled? So in this question, radius, what if the radius was doubled is asked as well. So if the radius is doubled, if R naught is 2R goes to 2R naught and R1 goes to 2R1, which is the inner and outer radius, that means that in this term, there won't be any difference because it is all in numerator and denominator, so the 2 cancels out. So that is what is mentioned here. The ratio, which is the epsilon, which is what I was talking about earlier, in the sense that these are the dimensionless numbers that we can use. So that remains unchanged. The term in the brackets remains constant. The lead coefficient contains R naught square, however, which turns out to be 4 R naught square when we double it. So the temperature difference del T between the inner and outer walls would increase by a factor of 4. So that is our answer for this one. And the third question for us is a Newtonian fluid flows downward in a circular pipe of radius r and length L. We have to develop the momentum balance to find the momentum flux profile, and from there we have to derive the velocity profile. Again, based on similar concepts, except for we are using rate of momentum here. So in terms of, we can use the rate of momentum in minus rate of momentum out plus sum of external forces is equal to 0. So pressure at Z is equal to 0 is P naught 2 pi R del R. Pressure at Z is equal to L is minus BL 2 pi R del R. And gravity, the forces, the sum of external forces, which is gravity, is rho G 2 pi R del R L. So we can see that in the equation here as well. Again, we divide by 2 pi L del R and take the limit del R tends to 0, and which we can manipulate into this final equation which is mentioned here, which is d by dr r tau rz is equal to del P by L into R, which is the pressure gradient as well, del P. So we can integrate this again. Now we apply the boundary conditions, which is at the center R is equal to 0, the stress must be finite. So here we can apply the logical boundary condition, because since R is in the denominator but tau has to be finite. So if R is in the denominator, then C1 goes to infinity, the entire term goes to infinity, and then tau RZ also goes to infinity. So by that logic, we can conclude that C1 is equal to 0 as well. So this is what the momentum flux profile looks like here. Then to get the velocity profile, we use the momentum. We use the Newton's law of viscosity to get a differential term for velocity as well. Again, similar procedure. We can integrate this with respect to r. At C2 at the wall, r is equal to r, which is the boundary condition. The velocity will be 0 due to the viscous forces. So from there we can find out C2. Then we can combine these terms to get a velocity term as well. So this is the Hagen-Poiseuille distribution, the parabolic velocity profile. So here we have derived the flux profile as well as the velocity profile. If we can derive the flux profile, then it's quite easy to go from flux to velocity profile. Now, this is the fourth and last question. So the problem is that this porous slab of thickness 2b generates heat via an exothermic reaction. SC as a function of temperature is given here. We have to identify the conditions under which the system reaches a steady state versus when it becomes thermally unstable. So again, we start out with a similar momentum balance, and from here we can see that we have already gotten dqx by dx plus c is equal to 0, which is basically dqx by dx is equal to c sc, which is again done by shell balance as well. So this is already quite similar to what we have discussed in the previous three questions. But the tricky part is this: since SC is also a function of temperature, which I have mentioned in the first question, we have to solve for that as well. So how we proceed with that is that we substitute Qx with k d square tx, k dt by dx, which is Fourier's law. So we substitute that, we get this equation. We substitute SC as well with the term that was provided in the initial question. We get this initial differential equation. So now we apply the boundary conditions. So at x is equal to 0, dt by dx is equal to 0 because of the symmetry. And at x is equal to plus minus b, t is equal to t naught, which is the fixed surface temperature. So we define dimensionless numbers as well here. So epsilon, theta and lambda. We can substitute these into the original ordinary differential. So again, this is something that we've been working on these past three questions, that to reduce the tedium, make it less tedious for us to solve, we use dimensionless numbers, and that way we get a very concise ordinary differential equation for us to solve. So we get this equation, simple second order differential equation with the transform boundary conditions, is that theta at 0 is equal to 0 and theta at 1 is equal to 1. In the question there is a hint that we can use this multiplication to get the to solve for the ordinary differential equation. So that is what we've done, and this is what the final answer is after resolving for that. So we take we identify the differential, and then we can resolve that kind of into the bracket as well. So from here on out, we get this d theta by d epsilon whole square is equal to 2 lambda e to the power theta naught minus e to the power theta. So we can take the square roots and we can integrate this as well to get a expression for lambda, which is important because we have to calculate the lambda at which it explodes as well. So we calculate lambda for various mid-plane temperatures. Theta naught is equal to 0.5, we get lambda is equal to 0.58, and at theta naught is equal to 1.12 or 1.186, we get lambda is equal to 0.878, after which it is decreasing. So it is kind of the maximum value that we get. So the system only has a steady state solution if lambda is less than 0.878, which is our maximum value. If it is greater than that, then the system would not exist. So that is the critical conclusion that we've come to using the math. The explosion condition, again, if the physical parameters are such that lambda is greater than 0.878, the heat removal cannot keep up with the exponential heat generation, hence it will explode. So that is the explosion condition that we've defined, which was asked for in the question. So the temperature will rise indefinitely, leading up to a thermal runaway or explosion. So the key takeaways, shell balances, we've done that in all the 4 questions that we've calculated, that we solved for. And again, dividing it by the surface area, taking the derivative and then integrating it for this constants is something that is that we've seen in every single question that we've done so far, even in class. And then again going from momentum flux to velocity flux, and then for with respect to the chemical heat sources part, we've discussed uh, SC and how it could be or could not be a function of temperature, and how to deal with either of those situations, which was in the first question it was not a function of temperature, and in the fourth question it was. So we've done all of that, we've discussed all of that. And yes, thank you for paying attention.